Had a nice lunch break? Very nice. Okay, we're going to wake up a bit as the time goes on. Hey everyone, I'm so excited to be here. App.js, Software Mansion, and Expo, thank you so much for having me. Before I tell you more about myself and why I'm here, I would like to tell you a story. A story about a React Native developer from an alternate universe. And in that alternate universe, React Native reanimated and worklets, they don't exist. They have never been invented. So that React Native developer goes on about their day, they're building their app, when suddenly their beautiful animations and interactions stutter, giving into tasks with higher priority. It's all running on a single thread, but as we know, devices nowadays have more than one thread, thankfully. But how do we make use of that? Well, a friend comes up to them and says, hey, I found this cool new library. It's called React Native RS Animated. It allows you to write Rust programs called worklets and dispatch them from JavaScript to run on the UI thread. Now, Rust is a great language. It's very type safe. It's very memory safe. So that sounds great. What could go wrong? Well, let's take a closer look at the API. It turns out that the API requires you to write Rust in a string. OK, nice start. And you might not be familiar with Rust, but we can see there's some variables there. There's like a main function there that's external to JavaScript. OK, it adds two numbers, writes them into C. And we can just run on UI, pass the worklet, and it runs on UI, apparently, right? But if we want to do more, we can use something called shared values, right? Use shared value. We have ABC, but now to hook the Rust together with the JavaScript, we have to give each value an indice, a number that identifies it. We cannot really refer to them by their name. It's not that high level. So we assign 0 to A, 1 to B, 2 to C. Very cool. We do the same in our JavaScript down below. And that's fine, but when the Rust code changes or the JavaScript code changes, we have to keep those in sync, so it's not perfect. And yeah, I forgot to talk about, we actually have to serialize our values into binary. When we create a shared value, we have to create a float32 array, or depending on what we actually want to share, an equivalent value. And that's fine for primitives, but for structs and arrays, that becomes much, much more complicated. So great, that doesn't sound tedious at all, right? And again, like Rust is an amazing language. And it's very capable. It's just the fact that we need to shoehorn it into a TypeScript code base that makes it miserable. We give up all of the type safety whenever values move from TypeScript to Rust or the other way around. And thankfully, there are alternate reality libraries that build on top of React Native RS Animated. But sometimes all you really want to do is to just run your own code on a different thread. Now, thankfully, we're in our own reality. React Native Reanimated exists. Worklets exist. But I really want to make the point that this situation is actually happening. This is happening in our own universe, just not with worklets. It's happening with WebGPU. WebGPU is the new cross-platform GPU API for the web, now also available in React Native, thanks to the amazing William Candillon. Ooh, yeah, round of applause. Yeah, it's so awesome. Like it really unlocks so much capabilities. Like it allows for more performant graphics computing, just general compute workloads for, say, you can imagine massively parallel computations like AI inference or simulation. And most importantly, it's not built on OpenGL, which has been deprecated on Apple devices for a while now. So what's the problem, right? It unlocks so many possibilities. Well, this is the kind of API you can expect, right? You have to learn a whole new language, which is kind of Rust-like, which is why I kind of drew that parallel. You don't have to learn it here. I won't require you to know or understand what it works. I just wanted you to see that the syntax is kind of foreign or can be foreign to TypeScript developers, and it's not ideal to kind of pull that into our existing code bases. And yeah, WebGPU sheeting language. It's the language that we use to write programs for the GPU in WebGPU, commonly abbreviated as WGZL. I'll probably use the Wiggle word from now on. And yeah, this is usually what you see in your actual code base. If you're integrating WebGPU into a TypeScript code base, usually just write it in a string, as I've shown in my alternate reality parallel. So in my analogy, React Native versus animated is meant to reflect the friction that a TypeScript developer might feel when using WebGPU directly. As an example, I want to show this shader. It's like an AI undulating orb thing that can react to your voice. You can think of it that way as a use case. And this is the code for it in WebGPU shading language. It's quite a lot, but I won't delve too deep into it. I don't want to teach you how WebGPU shading language works and how the shader works. So I'll just show you some TypeScript pseudocode. We have like a React component, and we say orb, and we just have a black sphere. And we can add some like props to it, let's say, like an ambient color, right? And it's pink, very nice. We can also add some Fresnel, which just adds like a rim lighting around the sphere, very nice. We can add like a light direction and diffuse, which gives it some more light from the top, some warm light. We can also change the background to a different color, very nice. What would also be nice to do would be to pass like a JS callback instead of a value so that we can react to stuff that's happening on the screen. In this case, the background callback receives a UV coordinate, which is just a 0 to 1, 0 to 1 coordinate on the screen. So in this case, we use the Y coordinate to blend between two colors, which in the end turns into a gradient that changes from the top to the bottom. Very cool. We're not there yet, but let's say that we took more time to develop this, or asked somebody else to develop these functions to plug it in. We could think that we could just import it from somebody else, plug it in as props, and it works, right? I mean, of course, I'm kind of lying here. I hid a lot of stuff. But just the ability to kind of take apart the orb, which is kind of the hard thing to actually draw the sphere and fake the sphere, from the visual look. You can separate those two apart. And I kind of lied to you. I'm a liar. This is not pseudocode, right? This is an actual React component that's written in plain JavaScript. You have callbacks. You pass them into the component, and then they get compiled into WebGPU shading language using the library that we're working on called TypeGPU. Thank you so much. Yeah, my name is Plaza. I'm the lead developer of TypeGPU. TypeGPU is one of the libraries created by Software Mansion, and basically what it is, it's a TypeScript toolkit for WebGPU, allowing you to write complex graphical and compute shaders without ever giving up on the TypeScript developer experience. It has no native dependencies, so it works the same way on web and on React Native, thanks to React Native WebGPU by William Candillon. And it's actually framework agnostic. I know this is a React Native conference, so this might be a little bit controversial. But it works with React, it works with Svelte, Vue, even just vanilla JS if you want to do that. And actually, the slides that you're seeing right now are just Vue components and TypeGPU using SlideDev, if you're curious. So let's back up a bit, right? Why should you care about TypeGPU? Let's try to answer that. Like, why build a new shader system at all? Like, we have so many cool libraries out there, right? Most in use by React Native developers are React Native Skia and Three.js through React Free Fiber. So where does TypeGPU fit into all of this? Well, if you think about it, all of the existing libraries like Skia and Three.js provide a high-level API, right, that you can like describe your scene in. But they also always provide an API that lets you drill deeper, an abstraction below, and lets you actually write shaders that work on a lower level and customize it a lot more. In the case of Skia, it's SKSL. In terms of Three.js, it's TSL. So for Skia, it looks a bit like this. This might seem familiar to what I've been showing before. You basically, because the Skia from Chrome has their own shading language, you have to write in that, pass it using as a string to their APIs, and it works. You have a great effect, it's cool. But it has the same problems as we saw before. If you want to build a bigger program and split it up into chunks, you have to concatenate it. It's not ideal, it's not something that we felt would be something we wanted to build upon. And in terms of Three.js, they have something called Three.js shading language, TSL. It looks a little bit like this. This is JavaScript, but instead of like saying a for loop, we have to say loop, like call a loop function, pass in the start index, the end index, the type of the variable, I think that's iterating, the condition as like a string, and then the function that gets called on each iteration. And like accessing arrays and stuff isn't, like it's not syntax that we're familiar with as TypeScript developers. And most importantly, this is not type safe. Like when you actually put this into a code base, you're not going to be able to hover over any element and see what its type actually is. You kind of have to guess based on the context yourself. So what we thought was, what if we just focused on those parts of those libraries? What if we build a solution that solves the problem of writing low-level shaders in an ergonomic way, sit down and research development for like 2 years, I think. And the result is a shader system that truly first class in your TypeScript codebase. Like feels like it belongs in your TypeScript codebase, and one that isn't bound to a specific framework. And I mean, that means you can write your shader functions once and use them across shaders, across frameworks, across your projects, across technology stacks. That's, I feel, really powerful. And most importantly, like we've built TypeGPU in a very modular way. So it allows you to build your own purpose-built framework, as we do in our examples page on typegpu.com, or integrate it into those libraries like Three.js or Skia, replacing their dedicated shader system. So why TypeScript? I feel like that's a question that gets asked to us a lot as React Native developers. Like, why? Why TypeScript? Why can't you just choose a normal language, right? And we're a little bit more tolerant to this kind of question, or like seeing TypeScript in places where it's a little bit unusual. But for us, it was more than just syntax. What it basically came down to was that it was easier to enhance TypeScript with the things that we thought were missing and that were in WebGPU shading language than it was to go the other way around. For example, Wigzil, WebGPU shading language, has operator overloading, which means you can add vectors, multiply vectors by matrices and stuff like that. You can't really do that in TypeScript, right? Right? We'll see about that a few slides from now. But TypeScript has importing from other files, right? That seems pretty important. It has generics. It has so many features we've come to be accustomed with. We also get to benefit from unified tooling, right? Our TypeScript language server is able to know about both the CPU code and the GPU code, and most importantly, keep it type safe on the bridge between that link. Yeah, I wrote console log there. I don't know if you guys have seen the tweet, but we do support running console log on the GPU, which allows you to be a lot more safer when you're debugging. You can just like console log on each pixel on the screen. Oh. And it works pretty well, I have to say. And it's very useful. Like otherwise, you would have to like draw a pixel and interpret the color of the pixel and see what's wrong with that. It's very hard to do otherwise. And also what I wanted to talk about is pre-computation. I'll touch on it a little bit later. But because of the fact that the code is the same, it's written in the same language and runs on both the CPU and the GPU, we're able to do something similar that web frameworks do nowadays with partial pre-rendering. You can think like you have the part of your shader / in this case, web page that's static. So you can just pre-compute that, serve it from a CDN, and fill in the dynamic parts on the client, right? That's very fast. You don't have to do all the work on the server or on the client. And we can kind of apply the same logic here. If we can do stuff before the shader even reaches the GPU, because it's in the same language, we can just run it, right, on the CPU, then we just generate smaller WebGPU shader code than you would write by hand. Tsover. What is Tsover? Well, Tsover is basically our fork of TypeScript. I know fork sounds pretty scary. but it's a sustainable fork. It's not like a usual fork, like you would think, like we fork a GitHub repo. What it actually is, it's a script that applies the changes, like minimal changes that it needs on any TypeScript version you want, and we just publish that as an alternate version of TypeScript that you can install. And what it allows you to do is it allows us, as TypeGPU, to define operator overloads for the things that we want. So you can have two vectors, add them together, and it works. You have type safety. And it not only works at runtime, so you actually get a real value. If you hover over C, it's a vector too. It's not any or throwing an error and shouting at you. And we built it as a separate solution so that you, as library authors, or if you want to just have operator overloading for your own objects in your app, you can just integrate Solver without integrating with TypeGPU. Of course, I want you to integrate with TypeGPU, but So to it's not just about syntax. I hope you can see why we thought it would be sane to compile TypeScript into WebGPU shading language to begin with. It's not just about syntax, it's about the developer experience and functionality we have grown accustomed to and we know the value of. And I have this half-serious claim that programs written in TypeGPU end up actually being faster than those written in WebGPU. Now that might seem crazy, because first of all, the shaders are in JavaScript, so that can't be fast, right? But second of all, we are built on top of WebGPU, so it's hard to think about how can we be faster than the thing we're building on top of. We're essentially limited by the efficiency of the WebGPU API. We even have an API, you don't have to read the code, but we have an API that's called tgpu.resolve, which just takes your TypeScript program, turns it into a WebGPU program. So theoretically, just the end user could write whatever we output and be just as fast, right? Well, that's the catch. It's human nature to cut corners. It's sometimes fun and satisfying to optimize things for the sake of it. But in the end, we're bound either by having to deliver something that works and is fast enough, or sacrifice readability and reusability in the process. And I've heard a lot of people approach general-purpose GPU programming as a last resort, meaning it's just simpler and more maintainable in the end to pull data from the GPU, which takes a long time, do computations in JavaScript, and push it back onto the GPU so that we can do some more calculations or draw it to the screen. And this is actually a huge bottleneck with libraries like ONNX runtime, which do AI inference. If a functionality cannot be hardware accelerated, the data is pulled back into RAM, processed on the CPU, and pushed back, which often ends up being as slow or even slower than just doing everything on the CPU. And going back to my note about pre-computation, which I kind of talked to you briefly about, I want to showcase you kind of the mental process of what that looks like. So here we have use GPU function. It's just a shader, accepts a parameter t. And we have a from color and a to color. We use the hex to RGB function, passing in a string to it with a hex code for a color. We have red and green. And then we multiply both values by half, so they get a little darker. And then we mix those two colors using the t that we got as an argument. Now, first of all, you can be kind of weirded out that there's a string in my shader. Why is there a string in my shader? This is actually a comp time function. You can mark any function you want as comp time. And what actually happens when we look at your code is this gets pre-computed before it even reaches the GPU. It's pre-computed in JS, so it turns into this, which is just read using 0 to 1 vector syntax. We then multiply it by 0.5 because both of those values are known, and this is it. We can't do any more about that. We do the same with the next line, and we end up with this. And then we just mix the two together because t is only known when the code actually reaches the GPU. So we can't really do anything about that at that point. So we end our process, and then we just turn it into WebGPU shading language. And you can see how the code is just very similar. The only thing really different is the syntax, but the actual semantics and what you wanted to achieve with your shader is kept as it is. And it was very important to us to maintain your intention as a developer. So essentially, I feel like we've reached a point with TypeGPU where, because your shader is just a TypeScript function, You're essentially writing the same code as you would if you were cutting corners, yet the performance is often better than what you would write by hand in TypeGPU, or with WebGPU, sorry. TypeGPU is the fast one. Now, I'm very proud that I've gone this far into the presentation without talking about the agentic elephants in the room. From the beginning, TypeGPU has put the developer first. And we believe that when we give developers powerful and expressive tools that reduce friction, amazing things can be built. Now, the side effect of this is that actually agents are very good at writing TypeGPU. We've recently released agent skills, which just fill in that gap of API, because TypeGPU is fresh enough that it's not really represented in the training data. But as we saw, like TypeScript is very well represented in training data, and agents are very good at writing TypeScript. So if we just tell them what the API is, they can do very well. And also using the fact that it's just type safe, and there's no like numeric indices here, numeric indices here that you have to synchronize. AI is very prone to like editing part of one file, but forgetting to edit the same thing in another file, and that can lead to very hard to reproduce and just track bugs. So that helps a lot. If you have one source of truth, AIs make less mistakes. And we have a few examples that were just purely made with AI. One of them is a real-time ray tracer. You can just like move objects around, and the ray traces in real time. And the other is just like a signal. It's called Signal Grove. It's like you have a field of grass and trees. That's what it's called. Yeah, and like water in something. It looks pretty cool. And yeah, it was interesting for us to do these experiments because we were thinking, like, wouldn't it be harder for AIs to build these, like, their own frameworks, basically? But it turns out they can build very good purpose-built solutions. And when they aren't limited by the expressivity of a high-level API, they can just tweak whatever they want. And thanks to the type safety, it just works. So finally, our AI slop can live on a type-safe foundation. Is it AI slop by that point? I don't know. And yeah, we love React, right? Software Mention loves React. And during the 2 years that we were developing TypeGPU, we were testing TypeGPU out in all sorts of React code bases. And we've gathered that up, finally, into a project that I'm very happy to announce, which is TypeGPU React. There we go. Now, this is still low level for the TypeGPU mythos, let's say. We're definitely planning to add more high-level APIs on top, but we also believe that with good primitives, people can build their own purpose-built higher-level APIs that suit their specific needs. So for now, we have a useRoot hook, which just allows you to asynchronously fetch a GPU device, which usually involves like a lot of use effects and not very maintainable code or code that can crash very easily. We also have resource allocation, which we found was very helpful, and just a use frame hook that doesn't require any re-rendering, which is very useful for performance. And it works out of the box with React and React Native, of course. My second to last point that I wanted to touch on. How's everybody doing? OK, very good. So, I mean, yeah, maybe you're excited. Maybe you know what TypeGPU is and why we did it, why we made the decisions that we made. But you might not be sure when you should actually reach for TypeGPU as opposed to the other solutions. And TypeGPU isn't really geared towards a specific type of app or effects. And because of that, I believe it's really a tool that allows you to get an intuition on how the GPU actually works, its strengths and its weaknesses. And it allows you to learn the platform and not the syntax or specifics of a particular abstraction. Now, not that I don't like abstractions. If you saw William's talk, redraw is a very powerful set of primitives that's actually built to work with TypeGPU and built with TypeGPU in mind. And I really, really feel that now we are in a time where abstractions don't need to own their own domain. They really can focus on what problems they want to solve. And redraw, it exposes a lot of primitives for high-performance UI elements with vector effects, and they can defer to TypeGPU for all the other stuff that makes the low-level access ergonomic. And because of this, I feel like now it's the best time for you to build your own primitives and share them with other people. I'm really looking forward to see what you're going to build. So when should I use TypeGPU? I feel like the question should actually be when to use the GPU at all. And to give you a very broad answer, if you're drawing anything, you should probably use the GPU, unless you want to experiment with a software renderer for some reason. That's also pretty fun. If you have a parallel algorithm, just some operation that you want to run on a lot of data, like a simulation, and you have thousands of objects, use the GPU. It's pretty good. It's pretty good at that. If you feel like you're moving a lot of data around, from the CPU to the GPU back, and you have to do processing on the CPU and push it back to draw it again, you should probably use the GPU. Now, if you don't have an idea for what you could do, you can look at our examples page. We have lots of examples, both graphical and compute, and including simulation, including the jelly slider that you may have seen on Twitter. And talking about the jelly slider, I feel like it's a prime example of what knowing the platform allows us to do. If Konrad Rečko, the author of Jelly Slider, was writing it in anything other than TypeGPU, I truly believe that he would quit halfway, because he would either have to debug mismatch issues that are irrelevant, really, to the problem when using raw WebGPU, or fight with a high-level abstraction to get the actual performance and result that he wanted. And I feel like TypeGPU is the perfect golden middle between abstraction and expressivity. If you have the App.js map and you're on iOS, that's very important, you can open up your map and you have a 2D to 3D toggle. The 3D map is written from the ground up in TypeGPU, so you can check that out and play with it, like zoom and rotate. It's pretty fun. And yeah, if you're already on, if you're already on Three.js, or you happen to like that abstraction, you can actually just use TypeGPU in Three.js already. You can look at our docs. We have a specific TypeGPU/3 integration guide. You can look at that. You can still use the high-level APIs that you want, but just use TypeScript to write you shaders. And on the topic of redraw, I know it's in technical preview right now, but if you want to get into it, you're probably going to end up using TypeGPU as the shader system anyway. You can already prepare for the publishing of redraw by trying out TypeGPU first, getting that intuition, and when it comes public, you'll just be able to transfer that knowledge over without any adjustment. So the last point. OK, you know where to use it, you know why to use it, but how do you actually use it? And for a while, that hasn't been super clear, because we've been adding just more and more cool tools that help you with that just the amount of steps grow and grow. So to help with that, I'm happy to announce another thing that we released not that long ago that helps with just that, and it's called the TypeGPU CLI. You can actually just run npx TypeGPU at latest, and what it's going to do, it's going to work like the Vite, create Vite CLI. You're going to provide your project name, select the template. We have the Vite and Expo templates. You can choose from our ecosystem libraries that implement some of the stuff already. You can even download the agent skills right then and there. So really, you don't have to think about anything. You can just run the command, set up your project, and start using TypeGPU. I love that word. And yeah, if you don't want to start from a better template, but you want to use some of our examples, like the jelly slider, and just play with it and see how it works, every example that you see on this page, if you click on there's a show code button, you can find it, and then when it shows up the code, there's an edit on StackBlitz button. If you click that, it's going to open up a new fork of StackBlitz. with that project. So you can either play with it on StackBlitz or download it locally and just start from there. And also, I mean, I feel like for a while to use TypeGPU, you had to know WebGPU and shader programming to begin with. And we really wanted to lower that barrier of entry. So we've started writing just bare fundamental guides, where you learn TypeGPU and graphics programming / compute programming at the same time as you learn the API. And yeah, we also have guides on how to integrate TypeGPU into other frameworks. And if your favorite frameworks is missing, just let us know, and we'll add it in. And if you hop on our Discord server, we're actually pretty active on there. If you don't get to scan the QR code, you just go on our typegpu.com, and there's this Discord logo in the top right. You can just click it, and you'll join our channel. There's a lot of people from outside Software Mansion just posting their projects that they built using TypeGPU, and it's very inspiring. And yeah, we would love to help you out with your GPU journey. And both me and Konrad will be walking around the venue, and we'll be happy to chat. Yeah, those are us, if you want to burn that into your brain. And my last point is math is cool. That's it. Thank you so much.